So in many different areas of mathematics and also outside of mathematics, usually we'll end up with some kind of structure that lends itself to be considered as a category, but sometimes these categories have some higher structure. Sometimes we can consider the morphisms themselves as objects in a new category, meaning that we can have morphisms between the morphisms, if you will. We call these two morphisms, and you can draw them by these two-dimensional arrows in the diagram over here. In this situation, we're really working with two categories. So formally, they are categories enriched in the category of categories. So that means that the home sets are no longer sets, but categories. In this case, we have objects, morphisms, or one morphisms, and so these two morphisms between the one morphisms. So these are the double arrows here below. And you can see how you can start iterating this, right? Next, you can try to enrich categories in two cats. So then the home sets will be two categories, and we not only have objects and morphisms, but also two morphisms and three morphisms. So in the diagram, these are the three-dimensional arrows between the two-dimensional arrows here. And you can keep going with this, and sometimes it's even necessary. Some examples, usually from a topological nature, they will naturally have some higher structure, even higher than three categories or above. But if you try to keep doing this iterative enrichment, this process quickly becomes unmanageable. There's just too much data to keep track of, too many coherence conditions that need to be satisfied. So it becomes a natural question to ask whether there's some kind of unified way of handling all of these n-morphisms in all these different dimensions simultaneously, which would then lead to a manageable notion of so-called infinity category. And at this point in the research, there isn't really one generally agreed upon definition of an infinity category. Many different definitions have been proposed. Some of them turn out to be equivalent to each other. Some we have not proven yet that they are equivalent. So that's why I would say that at this point, the theory of general infinity categories isn't really established in that sense. However, if we restrict to a special case, namely that of infinity one categories, then we really do have an established theory which is really well understood today. So what do I mean by an infinity one category? An infinity one category is a category, or an infinity category, in which all of the n-morphisms are invertible, starting from n bigger, strictly bigger than 1. So notice that I have put this in quotation marks. That's because this is not a well-defined mathematical object. So it's not a well-defined mathematical object until you give it a proper definition. And today, many different proposed definitions for this intuitive idea have been proposed and have also been shown to be equivalent to each other in the appropriate sense. So the most well-known are quasi-categories, complete Siegel spaces, Siegel categories, simplicial categories, and there are also others like topological categories, and even others. And at this point, basically all of these have been shown to be equivalent to each other. When I say equivalent in the appropriate sense, what I mean mathematically, I mean that they have equivalent model categories. If you don't know what a model category is, that's fine. If you do, even better. And the point is that you can consider them to be equivalent in some sense. Out of all of these, the quasi-categories are by far the most developed. This is due to the extensive work of André Joyal, who invented them, and later Jacob Lurie, who in his gigantic book, Higher Topos Theory, has really expanded this theory quite a lot. And since then, there have been many others who have contributed to the theory. So the quasi-categories are what we will be focusing on today. So here's an overview of the talk. We've had the introduction, that's finished now. And next, I'll formally, mathematically, rigorously define what a quasi-category is. It's based on simplicial sets, which I'll also define. And then next, we'll look at some aspects of the theory, some basic aspects of the theory, in particular at the homotopy hypothesis. And then mapping spaces, these are the generalization in the quasi-categorical sense of classical home sets in a category. And then limits and colimits, which generalize the classical limits and colimits, but in the quasi-categorical context. And then finally, we'll end with some examples. So, simplicial sets. To define a simplicial set, I need to define the category delta over here. It's a very simple category. The objects are all the possible posets like this, with brackets n, which are the posets of integers 0 to n, which is the natural order on them, classical natural order, for every n bigger than 0. And the morphisms in this category are just the order morphisms between them, so order preserving maps between them. And what is a simplicial set? A simplicial set is just a contravariant pointer on delta to my category of sets. So in other words, a pre-sheaf on delta. Okay, that's the abstract definition. How should you think about these things? You should think about these things as follows. A simplicial set is a collection of simplices of different dimensions which are glued together along common faces. So here you can see this, and on the right is red tetrahedron, a 3-simplex, is glued to this triangle along this point here. And this yellow triangle is glued to another tetrahedron, this orange one along this line piece here. So that's the geometric picture you should keep in mind when thinking about a simplicial set. I'll talk a little bit about how this abstract definition gives rise to this geometric intuition. First of all, for every n, every integer n bigger than 0, I have this object brackets n in delta, and this is set to a set in the category of sets by this functor x. So for any n, I have this set n, and I call this the set of n simplices of x. You should think about elements of this set as being n-dimensional simplices which appear in my simplicial set. And then the morphisms of delta, and in particular how x acts on those morphisms, will tell me how exactly these simplices are glued together. So the sets are just the raw data, and then the morphisms will give us how they are glued. Next, I'll denote the category of simplicial sets by this S set. So this is just a functor category. So the objects are simplicial sets, and the morphisms are just natural transformations between these functors. Okay, a little bit more about these simplicial sets. An equivalent way of describing them is as follows. A simplicial set is this family of sets xn, just like before, and it has some extra structure, namely given by the space and degeneracy maps. For every I in between 0 and n, here, I have a face map di going down in dimension and a degeneracy map going up in dimension. And what do they do? If you look at the geometric picture, well, implicitly all of these simplices come with a numbering on their vertices. So the vertices are ordered in this sense, and then di, it deletes the ith face, the ith vertex rather. It gives back the ith face of the simplex. So for example here, this triangle, di, if I apply d1 to it, I delete the first vertex, leaving me with this line piece here, which is the first face of my triangle. So it's by means of these face maps that I can express how these simplices are glued together. If I say that d1 of x is equal to d0 of y, that means that x and y are glued together along those respective faces. And conversely, you also have degeneracy maps. We go in the opposite direction. They take a lower dimensional simplex and interpret it as a higher dimensional simplex by copying vertices like this. Right. And then these have to satisfy some conditions. They're there for completeness, but I'm not going to go into them. Right. So the takeaways, we're working with a bunch of simplices which are glued together somehow. Okay, I'm going to focus on some special simplicial sets which will play an important role in, I realize I'm not sharing my camera, I think. I can still do that if you want.
Yeah.
I'll, sorry, people at home. Hello, here I am. Okay, sorry about that. Okay, so I want to focus on some special simplicial sets, which play an important role in the story. So let n be an integer bigger than 0, then I have the standard n simplices. These are just an ordinary simplex of dimension n, but then realized as a simplicial set. So how are they defined? They're defined by taking the hom functor on my object n here. So by definition, this is a contravariant functor from delta to set. So by definition, this is a simplicial set, and we'll denote this by delta n. And then if you apply Yoneda's lemma in this situation, this precisely means the following. So a map of simplicial sets from this special delta n to x is in one-to-one correspondence with elements of my set xn. so n simplices of x. So you should really view this delta n as like a prototypical n simplex, and a map from this n simplex to x is like a representation of my delta n inside of x. And indeed, this corresponds precisely to one single element of my n set, so one single n simplex. Okay, that's the abstract definition, but what I really want to focus on is the geometric interpretation, which is the following here. So delta 0 is just a point, delta 1 is a line piece, delta 2 is a triangle, delta 3 is a tetrahedron, and so on in higher and higher dimensions. Next up, we have the boundary. So for every n, I can take the boundary of my standard n simplex, and I can do this by removing the interior from my standard simplex. So another way to put it is by gluing together all of the faces, but leaving the interior out. So, for example, the boundary of delta 0 is just the empty set, empty simplicial set. Boundary of delta 1 is the union of these two endpoints here. Boundary of delta 2 is the edge of this triangle without the interior. Dimensions, it becomes difficult to draw, but this is a tetrahedron without the interior, so just a face. And then finally, the last of our main players are these horns. So for every j in between 0 and n here, I have the so-called jth horn, which I denote by this lambda, and I obtain this by removing the interior of my standard simplex and one of the faces, namely the jth face, by which I mean the face opposite to the jth point. For example, here, lambda 0, 2 here is the 2 simplex where I removed the 0th face, which is the face opposite to the 0th point. And similarly for these other lambdas, and in higher dimensions, you can do the same thing as well. So lambda 1, 2 would be this horn where I removed this face over here, the bottom face. Okay, so these are our main players. What can we do with these things? Before I get to the definition of quasi-category, I want to take a little detour to count complexes. These are very classical objects in algebraic topology. And they're defined as follows. So a simplicial set is a count complex or a space if it satisfies the so-called count condition, which means that for every j between 0 and n, every diagram of solid arrows in simplicial sets like this has a lift which is given by this dotted arrow. So there should exist a dotted arrow which makes this triangle commute. So just to be clear, this vertical map here is just the inclusion of the horn inside of the standard simplex. And this horizontal map, this can be anything. So it's if you will, it's a representation of the horn inside of X. So what this condition really says is that I should be able to extend any map from the horn to the entire simplex. And if I can always do this, then I call my X a count complex. Okay. Why are these things important? Well, they were introduced in the context of algebraic topology to give a combinatorial way of talking about topological spaces and in particular their homotopy types. So there's the following result by Quillen, which says that there's an adjunction of categories like this. So here's category of simplicial sets, here the category of topological spaces. And we can say that this adjunction identifies count complexes with CW complexes. CW complexes are especially nice kind of topological spaces, but only up to homotopy equivalence. So if you're only interested in spaces, topological spaces up to homotopy equivalence, then you can basically, the idea is that you can just as well take count complexes, which are of a much more combinatorial, a little more rigid nature, and are in that sense sometimes easier to work with. This is a bit of a vague statement. What I mean rigorously is that this adjunction is really a Quillen equivalence of model categories again. So again, if you don't know what a model category is, that's fine. It's not necessary for the rest of the talk. If you do, all the better. Okay, so we have this one source of examples, which comes from topological spaces. We can consider topological spaces as a special kind of simplicial sets, namely these count complexes. And another source of examples comes from categories, ordinary categories. So if I have a small category C, then I can consider the so-called nerve of C. This is a simplicial set, and its n simplices are defined as follows. So the set of n simplices of my nerve here is the following set, a set of all possible sequences of composable arrows in C of length n. So I take a sequence of length n, and these morphisms should all be composable, so the type and the source should correspond in the correct way. If I draw this out, if I draw out such morphisms and all of their conditions together, then you can really see the simplex shape coming back again. And this is the reason why this forms a nice simplicial set. So here, just the three morphisms and all the compositions form the other sides of my simplex set. So this is a good, well-defined simplicial set, and it satisfies the following nice property. So we can characterize the nerves as follows. A simplicial set is isomorphic to the nerve of a category if and only if, for every j strictly in between 0 and n, every diagram of solid arrows like this has a unique lift, which is this dotted arrow here. So notice that this is very similar to the condition we just saw for this count condition, I mean. But there are two crucial differences. So for one, we have that the j is only required to be strictly in between 0 and n. I only require these lifts to exist when j is strictly in between 0 and n. And on the other hand, I am requiring this lift to be unique. So I'm not just requiring it to exist, but I'm also requiring it to be unique. So this condition is both stronger and weaker in some sense than the condition that we just saw. So it's not so unnatural to ask the question, what if I take the common weakening of these two conditions? What if I take the common generalization of these two conditions? What kind of objects do I then get? And these are precisely the quasi-categories. So here's the definition. A simplicial set is called a quasi-category if it satisfies a so-called weak count condition, which means that for any j strictly in between 0 and n, any diagram of simplicial sets like this again has a lift. So you can see that here we're only requiring j to be strictly in between 0 and n, and we're only requiring the lift to be unique. So it subsumes the previous two cases. It subsumes these two influences, the category aspect and the homotopy aspect. And this is why we have the following slogan, the first slogan of the day, which says that infinity one category theory is like the union or the sum, if you will, of ordinary category theory and homotopy theory. So it's really baked in the definition, if you will. I want to hone in on this aspect a little bit. So how does this count condition, this weird lifting property with these horns, give rise to, on the one hand, category-like behavior, and on the other hand, homotopy-like behavior? So let me hone in on these two aspects of the theory. So let's fix some quasi-category, C, so a simplicial set satisfying this weak count condition. Then how does the structure of these simplicial sets give rise to some category-like notions? Well, the zero simplices of my simplicial set here, these are the vertices of my simplicial set. I can consider those as the objects of my quasi-category. And the one simplices, the edges which go between the points, I consider as the morphisms in C. And then you can think, okay, then the two simplices will be the two morphisms, right? Because we're working towards some kind of infinity category. And that's close, but not entirely accurate. It would be more accurate to say that the two simplices witness composition in C. So what do I mean by this? I mean the following: if I have two morphisms like this, f and g, from x to y and y to z, then I should be able to compose them. Right? And I will call h from x to z a composition of f and g if such a two simplex like this exists, so if it can be connected by a two simplex like this. And notice that I called it a composition and not the composition. That's because in general, in the quasi-category, I can have many different compositions of the same two morphisms. And at first glance, this might seem a little bit strange because in ordinary categories, there's one chosen composition of any two morphisms. But this isn't really a problem, and I'll explain in a second why. Another thing I want to emphasize is that now this count condition, this weak count condition, in particular for the case n equal to 2 and j equal to 1, expresses precisely that we can always compose two morphisms. Right? Because this shape, this is precisely a horn, and saying that I can extend this map precisely means that I can fill up this horn inside of my quasi-category C. So if I am encountered with some horn like this, I can always fill it up to an entire two simplex. In other words, I can always find some composition of f and g. That's what this count condition does. So we have objects, we have morphisms, we have composition, and then we still need identities to have some category-like thing. So the identities here are given by the degeneracies. So recall from earlier, we have these degeneracy maps. They take a point and make it into an edge in a degenerate manner. These will play the role of our identities. So that's the category theory aspect. Let's now look at the homotopy theoretic aspect. Because the same simplicial structure and the same count condition will also give us a notion of homotopy. If I have two morphisms, f and g, between two given objects, x and y, then I will call f homotopic to g if there exists a two-simplex like this. So f connected to g, where this is the identity, or equivalently f and g here, and the identity on x there. So basically, the two simplices play the role of a homotopy between morphisms like this. And then it follows from the weak count condition that this is actually an equivalence relation. So in a general simplicial set, this doesn't have to be an equivalence relation, this homotopy relation, but in a quasi-category, it will always be. So we get a nice working notion of homotopy in that sense. And similarly, you can use three simplices to define homotopies between two simplices, and four simplices to define homotopies between three simplices, and so on. So you really get a well-defined notion of homotopy on all dimensions. Okay, so these are the two sides of the story. There was one caveat, maybe at these compositions here. Right? I said that they're not unique. I also said that it's not a problem, and I'll try to explain why. Compositions are not unique, but they are unique up to this notion of homotopy that I just defined. So given two morphisms, if I take their composition, up to homotopy, there will only be one. And I'll try to explain a little bit why. Let's fix two morphisms, f from x to y, g from y to z, in my quasi-category C. Then I can consider the following pullback. Okay, I didn't define everything that's in here. It's not really that important. The point is that I end up with a simplicial set comp fg here. This is a simplicial set, so it has higher structure. It has vertices and edges and two simplices and so on. But if I look at the vertices of this simplicial set, these are precisely the two simplices, W and C, that fill in the horn given by f and g. I have this horn. This is fixed, and I look at all the possible two simplices which fill this up. These are the vertices of my simplicial set comp fg. So in other words, comp fg is the simplicial set of all possible compositions of f and g. We know that the composition is not unique, but let's look at all of them together, see what kind of structure we get. And then here's the nice thing about them. That is that this comp fg will always be a space, so a count complex, but think about them as a topological space. And not only will it be a space, it will be a contractible space. So that means that I can contract the entire space to a point. That's the idea. Formally, what this means is that I can also have this lifting condition similarly to before, but instead of having a horn, I now have a boundary of a standard simplex here. And I hope this is intuitively a bit clear. Recall that this boundary of my standard simplex, it's just a union of all the faces of a simplex. So basically, it's like the n-sphere, it's an n-dimensional sphere. Without an interior, and then this standard simplex delta n is like a filled-in ball, right? It has an interior. So saying that every sphere like this in my space can be filled up to an entire simplex basically means that whenever I have a sphere inside my space, it's actually part of a ball already, and this ball is obviously contractible. I hope that makes a little bit of sense. Another way to think about this is saying that all of the homotopy groups are trivial, which is another way to say space is weakly contractible. Do you have a question?
Yeah, this is not comparable to the counting.
No, it's similar in shape, but it's very different because of this, because we have the boundary here. Okay, so the point is that the space is contractible, which is like the simplest kind of space that you can think of. So in other words, the space of all possible compositions of f and g is contractible. We can have many different choices of compositions of f and g, but if I take all of them together, they form a contractible space, which is basically like the simplest kind of space you could want. This brings us to the second slogan of today, which is that uniqueness in ordinary category theory is replaced by contractibility in infinity category theory. Or in other words, equality is replaced by homotopy equivalence. Everything is only considered up to homotopy equivalence. Right. So you can really see the interplay of this category theory and this homotopy theory coming together. Okay, that's the basic introduction to quasi-categories themselves. Let's now talk about some aspects which come up in the theory. So first of all, the homotopy hypothesis. So the homotopy hypothesis was first, I think, recognized by Grothendieck, but he didn't use the term homotopy hypothesis. Homotopy hypothesis was Bayes, who coined the term homotopy hypothesis. And what is this? Well, it goes as follows. It says that infinity groupoids are equivalent to spaces. Okay, this doesn't make any sense. And indeed, it does not make sense because I put quotation marks around them, meaning that this isn't a well-defined statement. At least it's not a well-defined statement until you define exactly what you mean by infinity groupoids, by space, and being equivalent to. Depending on how you choose them, this hypothesis can be very easy to prove, right? If I choose infinity groupoids and spaces to be the same thing, then that's very easy. The thing I want to point out is that in the context of quasi-categories, you can make this precise statement, and it is shown to be true, and it's also not trivial. So I mentioned what a space was. These were these Kahn complexes from the beginning. I haven't introduced infinity groupoids yet, so let me do that. A quasi-category is called an infinity groupoid if every morphism from X to Y is an isomorphism. So it's similar to an ordinary groupoid. But what does that mean, an isomorphism in the quasi-categorical context? It means that there exists some morphism G in the opposite direction from Y to X, such that there are two simplices like this, meaning that if you look at the category theoretic interpretation, this precisely means that the composition of F and G is equal to the identity, and this precisely means that the composition of G and F is equal to the identity. In other words, it's precisely what you would expect an isomorphism to do, right? It has an inverse, which if you compose it with F in two directions, you get an identity both times. You have a question?
Yeah, the inverse is also not unique.
The inverse is also not unique, yes, exactly. But it is unique up to homotopy, as you might expect. And then it is a theorem by Joyal that indeed, in this context, with the definitions I just gave, that a space is the same thing as an infinity groupoid. So if I have a simplicial set, then this will be a space if and only if it's an infinity groupoid. One direction of the proof is very easy. If I start with a space and I want to prove that it's an infinity groupoid, all I have to do is fill in the required horns. So the count condition for the cases n equal to 2 and j equal to 0 or 2 allow me to fill in horns which look like this. This is the 0th horn, this is the 2nd horn. And I can make horns with my f, any arbitrary f I can put here, and here I can put the identity. And the count condition allows me to fill this up to an entire 2 simplex like this. And then with this 2 simplex, I get this G prime for free. This is a morphism going in the opposite direction. And this 2 simplex precisely expresses that the composition of F and G prime is the identity. And similarly, I can fill in this other horn, giving me this morphism G, which also precisely expresses that this is a left inverse of F. And then with some extra work, you can show that you can choose this G and G prime to be the same if you really want to. So this filling of these horns clearly gives an inverse for every morphism F. The opposite direction, however, is a lot harder. This takes a lot of combinatorial work, and this was done by André Joyal. This is also, I think, one of the theorems which really cemented quasi-categories as one of the viable models for infinity categories, or infinity one categories. So a lot of the basic work was done by Joyal. Okay, next topic. I am going to jump around a little bit in terms of content. The next, mapping spaces. So in an ordinary category, if I take two objects, then I have a set of morphisms between them. In this context, we won't have a set of morphisms between them, but a simplicial set of morphisms between them. So if I have an x and a y object in C, and I can consider, again, some kind of pullback. I didn't define everything that's in here, but the point is that I get a simplicial set, hom C, x, y, here, which will serve as my mapping space. I call this the mapping space of C from x to y. So this is a simplicial set that has higher structure, but the zero simplices of this simplicial set will be precisely all of the morphisms from x to y in C. So it does it on the zeroth level. It's exactly the same what you have in an ordinary category. But as I mentioned, it's a simplicial set. It has higher structure. So for example, it also has one simplices and a one simplex in this mapping space is an edge which goes from one point of my mapping space to another. But the points in my mapping space now are morphisms in C. So the one simplices in my mapping space are morphisms or edges going from one morphism to another. And how are they defined? Well, they are given by these squares in the original quasi-category C. So a one simplex in my mapping space is given by a square like this. I have F on the top, G on the bottom here, and identities on the sides. So notice that this is also very similar to how you define a homotopy in a topological space between two paths, right? And that's not a coincidence. So if you will, these one simplices of my mapping space, I could call the two morphisms of my quasi-category. It's one way of formalizing them, right? Because my mapping space has all the morphisms as objects, and the one morphisms of my mapping space are then the two morphisms of my original quasi-category. Okay, what's so special about this mapping space? Well, we have the following result. And if I fix two objects x and y, then the mapping space will always be a space. So I was justified in calling it a space all this time. In particular, it's a quasi-category. So you can also see how we can start iterating this. You can take the mapping space of the mapping space, leading to a notion of three morphisms, and then you could take the mapping space again, if you will. And these are still quite easy to describe. But I want to focus on the fact that it's a space for now, and not just a quasi-category, because this implies, by the homotopy hypothesis that we just discussed, that every morphism in my mapping space will be invertible. Right? In a space, everything is invertible. In particular, this means that all the two morphisms in my original C will be invertible. And this is why, in the beginning, I called quasi-categories a model for infinity one categories, because from the second level onwards, everything will be invertible. And this is formalized in the sense that these mapping spaces are always spaces, always complexes. What else is on this slide? I put this in here just because I could, just because it's easy now that we have these mapping spaces, because you could wonder what is the correct notion of an equivalence between quasi-categories, similar to an equivalence between ordinary categories. And one of the ways of defining it, one of the many equivalent ways of defining it, is by letting it satisfy the same two conditions that you would in an ordinary category, or in your ordinary category theory. Namely, it should be fully faithful and essentially surjective. What do these two things mean in the quasi-categorical context? Well, normally, fully faithful means that you have an induced bijection on the morphisms. Right? If you take the hom sets, then I should have a bijection on hom sets. In this case, however, we're not working with hom sets, we're working with mapping spaces. So the natural thing to require is now no longer a bijection, but a homotopy equivalence of spaces. That's the main difference here. And then essentially surjective is just basically the same definition as you would for an ordinary category. Nothing really changes there. But it's just very nice that this all works very similarly to the classical categorical context. All right, last topic, and then I'm going to go to examples. So limits and colimits in quasi-categories. So I'm not really going to discuss all limits and colimits. I'm going to specialize to a very special case, which is that of the initial object. And really try to explain what is going on there, try to give you some intuition about why things work the way they do. So let's first recall, in an ordinary category, an initial object is an object. such that for any object y, there is a unique morphism going from x to y. In other words, the hom set from x to y should be just a point. There's just one morphism going from x to y. But recall our second slogan of today, uniqueness is replaced by contractibility in the category. So the most natural thing to do is to define an object to be initial in a quasi-category. So now again, we're working in quasi-category C. If the mapping space is not a point, but is contractible. It's again the simplest kind of space that you can think of. It's a contractible space. And indeed, this turns out to be the right notion, which works very analogously to the classical initial object. So what does this mean? Concretely, again, the same lifting problem that we saw before when we encountered the comp FG, means that I should be able to fill any boundary to an entire simplex inside of this mapping space. And I have some time, so I think it might be worthwhile to analyze exactly what this means, at least in some low-dimensional case. Because this is quite abstract, I think. But if we take n to be some low numbers, n equal to 0, n equal to 1, then we get some quite clear statements. So, for example, if n is equal to 0, then the boundary of delta 0 is just the empty simplicial set. On top here, it doesn't really add any information. However, this delta 0, we do still have, and this is, as you recall, this is just a point, right? Delta 0 is just a point. And recall that a map from the standard simplex to some simplicial set is the same as picking out one specific simplex of that dimension, right? So in this case, this map just picks out one single vertex of my space. So saying that this map exists just says that there exists one vertex of my space, or in other words, there exists at least one morphism going from x to y, because the vertices of the space were precisely the morphisms from x to y. So this first case, n equals 0, just says we have existence, we have a map going from x to y. Then, if we go one level up, the boundary of delta 1 now, recall, is just the union, disjoint union of the two endpoints of this line piece. Delta 1 is just a line piece, and the boundary are the two endpoints. So having a map from these two endpoints to my space basically just picks out two vertices now, not just one. It picks out two vertices of my space. And again, vertices in the space are morphisms from x to y. So it picks out two morphisms. And having the condition that I can extend this map to a line segment means that I can that there exists a one simplex in my space which connects f and g. So in other words, for any two morphisms, any arbitrary two morphisms from x to y, there exists a one simplex in my space, but recall one simplices in the space are given by the squares. So for any two such morphisms, I can connect them with a square like this. And now we have this square. Look at what we have. Okay, because we're working in a simplicial context, this square should be divided up into two triangles. Everything is a triangle in this situation. We don't have squares. So we divide this square up into two triangles, and this top triangle here, recall, says that f is homotopic to this middle map here. This was precisely how we defined homotopy between morphisms. So f is homotopic to this middle map, and similarly, this bottom triangle says that this middle map is homotopic to G. So because homotopy is an equivalence relation, this means that f is also homotopic to G. Did you have a question? No. So we don't have a unique map going from x to y, but any two such maps are homotopic to each other. That's the idea.
Yes. I have a question.
Yes.
Because what do you actually have? Well, let's say there are two ways to have homotopy, in the sense that when you define it, you say that you have errors can be homotopy. So if you have a triangle which completes when two go inwards, but also two go outwards.
Right.
But here, if
you're using both.
Why don't you, in a sense, that because of G, we have that the downward arrow is homotopy equivalent to the identity?
Okay, yeah. No, so yeah, you should really take a look at how exactly these triangles were formed. I went by it quickly maybe, but the point is that there are two ways to define this homotopy, and both are equivalent to each other. So you can take either one, and both of these triangles, each one of them is one of those that we saw earlier. Does that make sense? So it's not the case that this middle map is equivalent to the identity or something. For that to be the case, this G should be the identity. Anyway, that's a little bit of a tangent there. The point is that if I take any two morphisms from X to Y, they're always homotopic to each other. And then we can go on, we can take higher n, and this lifting condition for these higher n expresses that these homotopies appearing in the previous slide, these two triangles, are also themselves unique, but up to a higher notion of homotopy. So if I have two such triangles that fit in here, I can connect them with each other with a tree simplex, with a higher dimensional simplex. So these homotopies are themselves unique up to homotopy, and those homotopies are again unique up to a higher notion of homotopy, and those homotopies are again unique up to a higher notion of homotopy, and so on, and so on, and so on. Except in dimension 10, no, that's not true. It goes all the way up. So that's what contractibility is. So what we've basically done really is the first situation is n equal to 0 expresses the existence of homomorphisms from X to Y, and all of the others express my uniqueness, but then in the form of contractibility. So if you will, I have replaced uniqueness with an infinite string of existences, if you will. Okay. Then a small word about general colimits. If you recall, a colimit is nothing more than an initial in a category of cocones. In the quasi-categorical context, you can do a similar thing. You can also define a category of cocones. So if I have a map from some K to C, where C is a quasi-category, then I can associate with a category of cocones, which is given by the C F slash. And in this case, we're requiring this mapping space to be contractible. So okay, I didn't define everything that's in this definition. It's also not that important. But the point is that, again, we're replacing uniqueness by contractibility, but instead of taking the ordinary mapping space, we're taking the mapping space of cocones. All right. I'll end with some examples. So one of the examples we've already seen at the very beginning is that if I start with a topological space, and there's an associated count complex that is phi infinity k. The notation is very suggestive, and so is the name. It's called the fundamental infinity groupoid. It's a generalization of the classical ordinary. Sorry, what am I saying? Yeah, fundamental infinity groupoids. It's a generalization of the classical fundamental groupoid of a space. And I like to talk about it by saying that it contains all homotopic information of X. What I'm referring to again is this identification that I showed at the very beginning by Quillen, that you can identify spaces with count complexes through this functor, up to homotopy at least. But concretely, what do we get out of this? A concrete consequence is that we can recover all higher fundamental groups of X from this fundamental infinity group. Right? It contains all of the homotopy groups as part of its structure, if you will. Another example, if I start with a 2 category, so it's like a smaller version of an infinity category, if you will, then you can associate with a simplicial set called the Duskin nerve, which was unsurprisingly invented by Duskin. And in low dimensions, it's defined as follows. So the zero simplices of this simplicial set are given by just the objects of your 2 category C. The 1 simplices are given by morphisms in the category C. And the 2 simplices are given by triangles like this, where the edges are all 1 morphisms in C. And the interior of the triangle itself, if you will, is a 2 morphism going from the composition of f and g to h. We're not requiring h to be equal to the composition of f and g, but they should be connected by a 2 morphism. That's the point. Now, in general, this is just a simplicial set, but if we require all of the two morphisms in C to be invertible, then this Duskin nerf will be a quasi-category. So we again find this behavior of an infinity one category where we require all of the two morphisms to be invertible. So only if I require this from a two category, the result will be a quasi-category. Next up, a little bit more advanced. If I start with a simplicial category, by that I mean a category enriched in simplicial sets, meaning that the home sets in my category are no longer sets, but simplicial sets, in such a way that I have a nice composition. Then I can associate with a simplicial set called the homotopy coherent nerve, invented by Courtier. And moreover, we have some conditions. So a simplicial category for any two objects A and B. We have an associated home set, which is not just a set, but a simplicial set. And if all of these simplicial sets are count complexes, then the resulting homotopy coherent nerve will be a quasi-category. This was shown by Courtier and Porter, again emphasizing this behavior that all of the morphisms from the second level onwards should be invertible. We can look at a very specific example. If I take C to be the simplicial category of count complexes, so the category of count complexes, and you can endow it with some extra structure, making it a simplicial category. And I can take its homotopy coherent nerve, and this is one way to define the so-called infinity category of spaces. This is an object that turns up time and time again, but when you're working with these infinity categories, it's a replacement for the category of sets within the infinity context. And this is one way of formalizing this. Next example, if I start with the DG category, C, then there's an associated quasi-category NDG of C, which is called the DG nerve. It was invented by Lurie in higher algebra. And later it was extended to also be able to take a nerve of A infinity categories, which is called the A infinity nerve, which is done by Ferrante. And then finally, we're getting more and more advanced as the examples go on. If I start with a model category, for those who know what that is, with a class of weak equivalences W, and there's an associated quasi-category denoted like this, also invented by Lurie. You could call it the infinity localization of a model category, or underlying infinity category of a model category, or something like that. So yeah, this thing exists. But the general gist about all of these examples is that whenever you have some kind of mathematical object which has some higher or homotopical structure, like a two-category or a topological space, anytime that I have this higher structure, you should be able to fit it into a quasi-category. So just like ordinary mathematical objects can usually be fit into a category or can be interpreted themselves as categories. We have a similar behavior here, and starting with objects which have some kind of higher structure to them. Okay. The person on the motorcycle outside is telling me to stop, so I will do that.